Okay. Yeah. Thank you for this introduction. And the detailed introduction makes my first two slides already obsolete. Um, just one point. The reason why I'm talking about storage is not only that our models are mostly used in storage, but I'm trying to coordinate the research on transport. I'm trying to coordinate the research on transport in the European Energy Research Alliance in the JPCCS. So that's that's mainly the background for this talk. What are we talking about? Now, when we talked about CCS 20 years ago, we were talking more or less about a concept where we connected one point source with one storage site with a pipeline. This point-to-point connection was relatively simple, but that's not what we are talking about today. Today, we are talking about what we call a multimodal transport network, having the idea that a European CO2 market will develop, that we're going to have pipelines connecting the largest emitters, but then also other modes of transport based on liquid transport in tanks, um, connecting smaller emitters to this pipeline or to the system, not necessarily to the pipeline, maybe also to ships, then delivering the CO2 to storage sites directly. Now, if we have a system like that, we can essentially distinguish four modes of transport. Um, there is the backbone, the pipeline backbone will be what we call dense phase pipelines, because supercritical sounds not right for the public, so we replace supercritical by dense phase. Um, we will have some gas phase pipelines, and we will have ship transport or tank transport on different pressure levels. What's relevant for you as the storage community is the pipeline, the dense phase pipeline transport, and ship transport or tank transport, whereby the pressure level doesn't really matter at that point. So that's the two kinds of transport that will connect this CO2 network to storage sites. Now, what are the purity requirements? Oh, at that point, it's important to have one thing in mind. When I talk to colleagues of yours about purity requirements of storage, I usually get an answer like, well, the requirements you're discussing in transport are very strict, and our storage sites will deal with that, except maybe for some site-specific issues. And that's the wrong answer. Because because if this becomes reality, we're going to have two standards. We're going to have a standard for dense phase pipelines and for ship transports, and storage sites which don't come up or which cannot deal with these standards cannot participate in the CO2 market. No? That's a requirement. And theoretically, you can still post-process the CO2 before it's stored. For particulate matter, that's realistic. For anything else, I think that's unrealistically expensive. So if there are concerns with regard to impurity, articulate them, because there will be standards which are valid for the whole system afterwards. That's important to have in mind. Now, what are we talking about? There's first of all the discussion on purity. So people talk about 99.8%, 89% CO2, 95% CO2 as minimum purity. When we talk about these purity levels, the balance essentially are what we call non-condensables, and that's mostly nitrogen. So that's the balance between these 95% CO2 and 100%. Why do we care for nitrogen? Now, what happens? This is pressure temperature diagram. The blue line is the vapor pressure curve of CO2. And when you start adding non-condensables, 1% nitrogen, you see that the saturated liquid line is shifted to higher pressure. 2%, 5%, 10%. This is relevant for pumps and equipment, of course. But the most important point is that if you have a small leak in a pipeline, the pressure, the CO2 is going to expand until it hits the saturated liquid line. And then it goes into the two-phase region. And in the two-phase region, the speed of sound is much lower than in the liquid or in the gas phase. So it's likely that cracks move faster than the decompression wave. And that's what we call running ductile fracture. And that's something pipelines need to be designed against. So if you have more nitrogen in the CO2, you need thicker walls, the pipeline, to be safe against running ductile fracture. And the thickness of the walls limits the maximum diameter of a pipeline, right? Because the thickness is more or less proportional to the diameter. So with more nitrogen in the CO2, you cannot build pipelines with a large diameter. The diameter of the pipeline shrinks, right? And that's the balance we are discussing when we talk about pipeline transfer. So I was pretty satisfied that in Europe, in the US, we have this 95% limit. In Europe, we were more or less set to say we need 98%. That looked like a good compromise to me. However, low nitrogen levels mean that processing, post-processing of the captured CO2 becomes expensive, in particular for oxy-fuel processes, for cement industry, waste incineration using oxy-fuel processes. And what has started now is a discussion: where is the optimum in the chain cost? Shouldn't we allow for higher nitrogen content, go back to 95%, knowing that the pipelines get more expensive, but having cheaper post-processing? Now, in principle, I agree that minimizing the chain cost is what we should do. But at that point, the discussion at the moment is focused on capture, post-processing, and transport, and storage is left out. So the question to you is this relevant for storage? Will larger nitrogen contents raise the storage cost? And that's a figure here, density plotted over nitrogen content. Sorry, one too far. And what you see is that with increasing nitrogen content, the density decreases. Of course, there's an additional effect because now you also store nitrogen, but the density of the mixture decreases with increasing nitrogen. At high pressure, this effect is not very pronounced, but there is a pressure range where this effect is very strong, and that's because a nitrogen-rich gas phase is built. So 7-8 megapascal at 300 Kelvin, to me, this sounds like a shallow natural gas reservoir, depleted natural gas reservoir. So my guess is there will be reservoirs where this effect is very strong, where nitrogen plays an important role, while other reservoirs, the effect will be relatively small. So if we look at higher temperature, more like a deep saline aquifer, what I would expect, there still is an effect, but it's much, much less pronounced. So we need input from your community. What is the increase in storage cost when we increase the allowance on nitrogen content? And this should be articulated because it's an element of the chain discussion we are leading at the moment from the capture and transport side. Now, in most cases, when we talk about saline aquifers, of course, there will be water involved. So we do not have only the system CO2 nitrogen, we do have a system where water is involved, but that doesn't make a big difference because the nitrogen is anyway solved in the CO2 phase. And close to the injection site, you will have two separate phases, a water-rich phase, a CO2-rich phase. So that's, at least to my understanding, that doesn't make a big difference whether we have a dry or a water-rich system. And then there's the other category of impurities. where we talk about ppm range. And that's largely independent of the total impurity. Whether we have 99.8% total purity or 95%, there's always enough space for a few ppm of water and SOx. The first impurity is water. That's relevant at that point. And that's relevant for transport, always due to the formation of corrosive phases. So we need to avoid the formation of corrosive phases, mostly in pipeline transport, but also in tank transport. For water CO2 system, we have a pretty good understanding. So there aren't many open questions. But we are still talking about a few hundred ppm or even 1,000 ppm when we only have the system CO2 water. The only thing that might be relevant for storage at that point, because your reservoirs contain water anyway, the only thing that might be relevant is hydrate formation close to the injection site when the temperature drops. That might be an effect that can be critical for injection, but we do have models which describe that reasonably well. So we know at which temperatures hydrates are formed, so that can be described. But then there are these impurities which are where we are really down to a ppm level. So sulfur oxides less than 10 ppm, nitrogen oxides 1.5 ppm. That's the Northern Light specifications. And even though this is for liquid transport, it's very often used in the discussion on pipeline transport as well, which is, of course, not correct, but it's very often used for both. And Aramis has published specifications both for pipeline transport and for liquid transport. And you see that more or less this is an agreement. There are discussions whether we can allow for a little more NOx when we reduce SOx further, because removing SOx is cheaper than removing NOx. So there are ongoing discussions, but in any way, we are talking about single-digit numbers. And my understanding is that this should not be a challenge to storage sites. Even if this gets in contact with the cap rock, it's so little, so there won't be much of an issue. It's a problem for pipelines because we got aware, thanks to work of IFE mostly, that there are chemical reactions going on in the pipeline which you would not expect at ambient conditions. In this pipeline environment, you have chemical reactions which in the end lead to the fact that every sulfur you have in the CO2 ends up as sulfuric acid. And NOx ends up in nitrous acid. The critical issue is the sulfuric acid, and that's a no-go. You can't have sulfuric acid in a pipeline. The corrosion rates will be far too high to be controlled, so that needs to be excluded. So that's what we are discussing at the moment and what we try to understand, and where we have indicative measurements but not a full understanding of the system. So we cannot define the optimum yet. We know points which are safe, which can be operated. Defining the commercial optimum is still a task that's open. There is one other issue which I don't like and which I would like to mention, because there is a risk that similar things are formulated from your community as well. If you look at these specifications, you have a lot of components where the limit is 0. And there is nothing like a 0 concentration. As soon as you have a waste incineration plant in the system, it's only a question which analytics you use, you will find everything. We know from ThyssenKrupp that they have found 2,000 components in their CO2 when they started to look really at detail with all the lab equipment they had. Huh? So, so zero is not a valid definition. I think among us, we can easily agree that a few ppb is zero. But I'm very sure that we're going to see legal debates when, as soon as we have failure in some processes, that people start to claim that the CO2 have been off spec because a few ppb of something has been in it, and that was supposed to be zero. So we need to get away from these zero limits. We need a small but quantifiable level, not for engineering reasons, for legal reasons. Huh? And that's something that's also my message to your community when you start thinking about allowable compositions for storage. Avoid zero. Zero is not a valid concentration. And we have to solve this for the transport community, which will take some time. Yeah, that's it. And thanks for your patience.